there have been 3 revolutions in quantum theory. The first revolution, 1900 to about 1970 something, was the one you all learn about. You know, Max Planck, Einstein photoelectric effect, Planck black body radiation, Einstein photoelectric effect, the Bohr atom, Schrodinger's equation, Heisenberg matrix mechanics, and Dirac electron, and then Feynman and Schwinger, the Feynman diagrams, quantum electrodynamics, all that stuff you learn about in school, and how to calculate atomic physics, solid state physics, the Bloch, the energy band theory, all that stuff. And that's all correct, that's quantum mechanics. Then, starting according to David Kaiser, my group of pirates, renegade physicists, starting around early 1970s to about now, to about 2015, was, according to the book, where is that book? Yeah, can I, according to David Kaiser's book, How the Hippies Saved Physics, our little band of misfits, we created the second quantum computer, quantum information revolution, because we were, in fact, I was already, I sort of discovered a precursor to Bell's theorem in 1960. Okay, back in 1960. When I was an undergraduate, I studied with Hans Bethe, who was the head of the theoretical physics division of Los Alamos, and also, he was my tutor my senior year at Cornell. And in the summer of 59, I guess it was, I read David Bohm's textbook, Quantum Theory, which is the book he wrote about Bohr, the Bohr Copenhagen interpretation, and not his later hidden variable theory. This is just conventional quantum theory. But in that book, a couple of things. There's, I think, chapter 8. He talks about how the quantum wave function is very like thought, how things in quantum theory are similar to psychology, the psychology of consciousness. That's already in David Bohm. And by the way, Bohm got this, Niels Bohr, this is actually an old idea. It's not really a crazy idea in that Bohr, Heisenberg, by the way, I knew Heisenberg personally. They were all kind of, in a vague sort of way, that the quantum wave function is, has something to do with thought. In fact, Wigner and von Neumann and Fritz London, they all have this idea that that consciousness collapses the wave function. So it's all very, I mean, if consciousness is collapsing the wave function, clearly there's some relationship the wave function to mental stuff. Then you have James Jeans, back in the 20s, I think, maybe the 30s, he said, the universe is looking more and more like a great thought rather than like a great machine. Well, what's he talking? He's talking about the quantum waves. Okay. And also, when I was learning quantum mechanics at Cornell, I mean, they didn't even think of information. It was just like the wave function, well, probability maybe, but they didn't get very deeply into the meaning of quantum theory. Just, like shut up and calculate. But also in David Bohm's textbook, he talks about the EPR experiment, and he had changed it from particles from momentum and position correlations to Stern-Gerlach magnetic moment spin correlations, which was a nice way. But then, so that kind of fascinated me because, hey, this is kind of weird. I mean.
And then, Jack, did you study with Bohm after that?
Well, after, but that's years after. I'll get to the timeline. But the thing is, no. But then what happened was, I got the Brandeis. I had a National Defense Fellowship to Brandeis. Everything paid for, Title IV National Defense, and while there, I ran across a paper on the tau theta puzzle. It was in Reviews of Modern Physics, like this is 1960, and there they're talking about, and it just dawned on me, hey, wait, this contradicts relativity. This EPR, it seems to contradict relativity. And I went to Sylvan Schwaber and Stanley Desser, and I said, hey, what's going on here? And they got very upset, because I guess they didn't realize it themselves. They said, basically shut up and calculate, don't think about it. And I said, this is important. But I was basically beginning to think, like, this is 1960. Bell did his thing in 1964, okay? And I sort of got pissed. I actually quit my fellowship after about 2 years. I quit the fellowship, and right away I was recruited by the CIA well, I worked for a place called Tech Ops, and they were on Route 2, Lexington, Massachusetts, around there, and they were doing work for the CIA on high resolution, the satellite cameras, for surveillance, that kind of thing. And while there, I was working with this guy George Parent, and a whole group of they were classical optics guys. They worked with Emil Wolf at the University of Rochester, classical optics, and they didn't know much quantum theory, so they hired me. I was like 21 years old, to learn, quantum. Lasers. Lasers were just coming in. They had a laser, but it was very early. This is 1963 now, by around 1963, the lasers. And so they had me working on this, and I wrote my first paper for the Italian, publishing the Nuovo Cimento, Italian Physical Society, appropriate since my name is Italian, Sarfatti. But it was on quantum mechanical correlation theory of black body radiation. Correlation, it was a trivial thing today, but back then, nobody, they didn't really know. And they wanted me to work with Paul Roman to finish my PhD at Boston University. With a guy named Paul Roman, who was part of the professor there, part of their group. But in any case, I went back to Cornell, and then again the intelligence services, I guess, manipulating. And what happened was I was offered a summer job at Ford Philco Aeronutronics in Newport Beach, California, back in the summer ~63, at an amazing salary of $1,000 a month, which I, for a 21-year-old, and so I could, carry it off. I couldn't refuse coming to California anyway. So here I was, about 22, 23 years old, living in Laguna Niguel, with an XK150 Jaguar from Hollywood Sports Cars, young and good-looking, and dating Hollywood starlets at the Beverly Hills Hotel. And this was also a government security, Ford Philco Aeronutronics. And that's when I met Richard Feynman. So, because we used to go up to, from Newport Beach up to Caltech. And I didn't really know who Feynman was at that point. And Feynman is there in the hallway, up near in the hallway, whatever. And he's talking, he's talking, this whole crowd about him, talking about superfluid helium and coherence and stuff like that. And we got to know each other, and right away we kind of clicked. And that day his car was in the repair shop, So he said he needed a lift, so I said, I'll give you a lift. And then I took him, and he saw this this Jaguar XK150 black with white leather interior and top down, and the spoke wire wheels. And so he said, so we got into the car, and he said, hey, we took a little detour. There was no hurry. We were going down Sunset Boulevard, and he's flirting with girls, and then we went into a topless bar, the whole thing. So those were exciting times. But then what happened? Okay, I finished my thesis I was in La Jolla, UCSD. Also, I worked with a guy from UCR, although I did all my graduate work at UCSD in La Jolla. I became an assistant professor, I was about 27, at San Diego State. Okay. And then, the strangeness happens again. And it turns out it was a CIA thing. Oh, yeah, I should mention this, that when Kennedy was assassinated, I was at Ford Philco Aeronutronics, and the way everything was. And at that point, then I volunteered to go into the CIA. And I was interviewed. They had me go up to Westwood, and I spent several hours at a room with all the tape recorders going, and I never heard from them after that. I had security clearance working at Ford Philco, and but then so now it's 19. When was it? 19. Okay. Well, first of all, about 1966, I was contacted by the British. And I spent a couple of summers at Her Majesty's United Kingdom Atomic Energy Authority at Harwell, Didcot Harwell, near Oxford. And at that point, I met, I used to go down to Imperial College, met Abdus Salam, and people, the Higgs, the Higgs gold. I met Goldstone, and I think it was Higgs. I met all these people, into spontaneous symmetry breaking around 1966, and then in 1971, what was it, 1971. Then I went to Birkbeck, and did postdoc work at Birkbeck College with David Bohm. Although at that time, Bohm was not into his hidden variable theory. He had sort of forgotten about it. In fact, the guy Basil Hiley, who was his assistant, said he didn't even know, when we were together, he didn't even know about the hidden variable theory that he did with Einstein, in '52. He didn't even know that. Bohm was so, cowed by the establishment, because it was considered sort of crackpot stuff, that he didn't even talk about it back then. It was only later that Basil Hiley got back into it. And okay, so with Bohm, and I also at that point I was with I took the Twister. Roger Penrose was also there, and he was a young professor before he went to Oxford. And so I took a several month, just a seminar, 2 or 3 guys, 4 guys, 5 guys on twisters. Though I didn't understand much of it, but okay. All right. So that was okay. So then the weirdness happens. I'm back at San Diego State from Bohm, and I'm with this guy. I'm a young assistant professor with this guy, Fred Allen Wolf. Some of you may have. He's in What the Bleep. But Fred Allen Wolf and I we had joined. He was associate professor. I was an assistant professor, and we had adjoining offices next to each other in the physics department. And he gets a call, and also we both got divorced. We both, Fred was a very straight guy, Bermuda shorts, short hair. I mean, that looks like Allen Ginsberg. But back then, he was driving an Austin Healey, Air Force contracts. He was like, he had, worked at the, all kinds of defense connections. San Diego being a Navy town, defense town. And but we had both gotten divorced, and we moved in together at a little apartment right at the edge of the San Diego State campus. And the women at San Diego State are just gorgeous. I'm 32 years old. So we were having a good time. And then Fred suddenly gets a call from an old high school friend of his called Bob Tobin, who's an artist who apparently made a lot of money on the commodities market. He's from Chicago. And Bob shows up, okay, and says, hey, listen, guys, he wanted to see Fred. He said, because he was so interested in this guy named Uri Geller, this Israeli guy. Uri Geller is able to bend metal, and this and that. And he had a book contract, and also a TV book contract with Dutton to write a book, and wanted to know if all this weird, bending metal with the mind and all that kind of stuff, if that could happen, how would physics, is it supernatural? So that's what we said. Okay, so right around this time, 2 things happen. Fred gets a phone call from Paris. A friend of his at the University of Paris, Fred does atomic physics, and they invite him to come for a semester, somebody, one of their guys was on sabbatical, and they have like a teaching in his field, and just to come for a couple of months to Paris. At the same time, he gets another call from John Hastert, who was the head of the physics department at Birkbeck, where David Bohm is, where I had been too, saying they also had a thing there, so he could commute back and forth between Paris and London. He has like 2 teaching gigs, right? He was going to take a sabbatical from San Diego State. Simultaneous with that, and Fred and I living there, I get a call from Abdus Salam. At that point, Abdus Salam was the head of theoretical physics at the Imperial College of London, and he was also director of the UNESCO International Atomic Energy Authority Institute for Theoretical Physics in Trieste, Italy, which was the meeting ground for Russians, East Europeans. Remember, this is now 1970. This is the height of the Cold War, right? And guys from India, Middle East. I mean, all this was a thing. And Trieste is right on the border, of Yugoslavia back then. So this was actually well known. Actually, there's a movie with with Robert De Niro about the trainee or something, and it's about this. I mean, it's a synchronicity where that institute is mentioned, and it is like a ground for all kinds of Cold War on both sides, intrigue. Because I was with these physicists. In fact, we were invited to I went into Yugoslavia, Ljubljana, the Nuclear Physics Institute there. Fred went into Bulgaria and got into an affair with the daughter of the head of the Bulgarian Secret Service. It was, in any case, I later found this was all part of a CIA operation. This is when I got involved with the remote viewing and the CIA experiments with Uri Geller, Ingo Swann, remote viewing, and that led into the post-quantum theory, which explains all that stuff. The point is, in the post-quantum theory, we have more information. We have the final information and the initial information. We want to know what happens in between some initial condition and some final condition. It's like teleology. Okay, and the rules of doing quantum theory are changed. We now have at the post-quantum level, it's not a statistical theory yet. God does not play dice with the universe in post-quantum mechanics. Einstein was looking for this. He said, I do not believe God plays dice with the universe. However, what stopped him from realizing this was that he only believed in retarded causation, that past cause, present effect. He was not willing to consider as a reality, as a possibility rather, future causes of present effects. Okay.
Can I ask you a question?
Yeah.
How does the retrocausality principle, and when you're rewinding that boundary condition, how does that lead to the quantization of the gravitational field that you described?
No, but the point is you don't quantize the gravity. Okay. Well, I actually, I think I'm going to almost answer your question here. So let me get to this. Okay. So normally in doing ordinary quantum mechanics with Hermitian operators and unitary time evolution for closed systems, you have what are called Hermitian operators. And you have some kind of quantum wave function, quantum state, and you want a statistical expectation value. Okay. Now, I'm going to show you, this is the post-quantum mechanical, I don't know what to call it. It's no longer a statistical, there's no statistics yet. There's no quantum statistics. This is just an individual particle or individual system theory, okay? But this is, you have something which I don't know what to call it. I'll call it the weak value, because that's what Yaki Aharonov calls it. So if I have some local operator that's defined at a point in space and time, let's say a local operator, I'll call that A caret, this is standard notation, A at X, okay, the space, with a subscript W, okay. The definition of it now is this. F is your destiny back from the future state. I is your history, ordinary, propagating forward in time, and X, you can think of F and I are like here, and we're looking on a space-time diagram. This is time, so history state there, this is the future state, F there, and we want to know what happens at an X in between. Okay, that's the problem, okay? So this is the Yaki Aharonov definition. It's this, yeah, all right? The typical, I'm using Dirac notation, you all know that, right? So this is it. This is non-statistical. God's not playing dice. So the question now is, how do we get to...
Yes. You're taking your expectation value, so that's statistical.
No, it's just right now it's algebra, inner product. It's an inner product. It's not statistical. I'm going to just wait. I'm going to show you statistics. The next step is statistics. This is just something I can calculate this formally, okay? This is... this will be the, okay, what this is physically, okay, good question. Physically, this is, if you were to do a weak measurement, and there are techniques for doing that in the lab, if you were to do a weak measurement of this observable A at the point X, individual, for not an ensemble, that's the thing, you're not averaging over ensembles, just at a single, like you're looking at a single electron in those ion traps and things like that, okay? If you were to just measure that, say the position of that electron in that single electron, no statistics, that this is what you would get. This is what you expect to get All right. Now let me get back to what you're familiar with, the familiar ground. In order to do that, you have to now add an axiom. Post-quantum mechanics is a bigger theory. It's okay. Think of geometry. Think of geometry. Euclidean geometry has 5 axioms. Okay, right? So think of you're doing geometry, which are only the first 4 axioms of Euclid. Okay, and now you're coming to the 5th axiom: what to do, how many lines parallel to a given line pass through a point not on the line. Okay, and you have some choice there. In fact, that's how you got non-Euclidean geometries, right? By changing that. Okay, but now, so this is analogous to Euclid's 5th, in terms of the logic of the theory. You now introduce statistics, a statistical part. It's an axiom, like your code theoretic. It's an ansatz. Okay, so you assume that this is basically the Born rule. You assume that the probability, the conditional probability between I and F, is the square of this. You assume that. But now look how beautiful this is. So now we're going to assume just what he said. Suppose we don't really know anything about the future. Okay, all we know is the past, right? So what we have to integrate over all the possible future conditions. That's like taking a partial trace of a density matrix. Basically, the same idea. Okay, so look what happens if we weight it by the Born. We've assumed now the Born rule. It's basically quantum mechanics, right? We assume the Born rule. So if you just do the integral over f, all values of f, this is what you get. Yeah, it's just algebra now. And because of the orthonormal completeness of the final states, that's 1, and you get this. What's happened? Well, now this is forward causality. There's no backward in time anymore. We've integrated it out. And all we have is the typical forward in time effect. Now, but that's still not the expectation. We have to do one more integration. Now, normally, when you're doing quantum mechanics, you then integrate over x, or over all x, to get the expectation in the state. You integrate over x, right? That's what you do. And so we use the orthonormality again, and this is quantum mechanics. So we have a beautiful, very simple, elegant, how the bigger theory, PQM, limits to what you're familiar with. And everything that Remy does, when he does his any quantum mechanics, they're working at this level, a statistical level. But there is this hidden reality here. Now,
Wait a minute.
yeah.
How do you know the domain of integration of f?
What, pardon me?
How do you know the domain of integration of f?
Well, I'm assuming, I just did it. I'm assuming that, we're assuming the rules of quantum theory that we have a complete set of states, and if you make that, I've assumed this. That's, you're not going to question that, right?
No, but that's just a statement of orthonormality, right? But
No, and completeness. I'm assuming that the future wave functions are a complete set of states. I'm assuming, if you don't like that assumption, but then, if you don't like that, then you better not like it for the past either, because it's time symmetric. So if you assume it for one, you got to have it for the other. In any case, I mean, you could object to that, but I don't think many people worry about that. I mean, it's beautiful. I mean, this is standard quantum algebra. Okay. Well, yeah, we're assuming that the future is a complete. If you assume that in the past there's a complete set of initial states that you could integrate over, then by time symmetry, which is basic assumption here, it's the same as the future. This is the block universe of relativity. It's basically Einstein block universe. What Einstein said, the distinction between past, present, and future is a stubbornly persistent delusion or illusion or something like that. So that's.
Do you think he grasped your question? Because there's always.
Yeah, I grasped it.
No, I don't know. Not obvious. But
Yeah. Okay, if you don't, but then you have to come up with a new theory as to why that shouldn't be the case. I am assuming that.
it probably requires a little more discussion and talk.
I don't think so, because right now I've shown if you make that's an assumption. I'm making an assumption. Okay, making an assumption. But it's an assumption that a lot of people make. I mean, it's not like it's a far out crazy assumption. I'm assuming that what works in the past also works in the future. That's part of the whole time symmetric retrocausality idea. And if you assume that mathematically, this is a rigorous derivation. And it's simple. Yeah.
Quantum mechanics, you have
What?
in quantum mechanics, you have some state, some transition probabilities.
Okay, right now I'm just taking expectation. I'm not doing transition. I'm just doing now the expectation value of an observable in a.
Doing an ensemble average.
Yeah, this is the ordinary ensemble average. This is, I'm not doing perturbation. I'm not doing quantum jumps yet or anything like that. That's, I just want to show. What?
You have some state, another state, and you are interested in understanding the transition probabilities from the two states in the past and in the future.
Well, that's this.
Yeah, like.
That's that. I assume that. Okay. In any case, just look at it purely mathematically. Do you see the logic and the consistency of the math given the assumptions? And then we could question the
more general framework you're saying is just to look at the inner product space before any norm space, anything. So the pure inner product is the deeper theory.
Yeah, right. And in terms of what it means physically, it has physical meaning in terms of the weak measurements, which is the whole experimental thing. Which to learn about some of the actual experiments measuring these sorts of things, I'll send the thing an email. Ephraim Steinberg is experimental physicist at the University of Toronto, has all kinds of beautiful, showing how this really is practical in the lab. If you're doing a double slit experiment with an electron beam, okay, and you see the far field interference pattern, okay, those are strong measurements. But these experiments have actually been done, okay, in the lab. It's not hypothetical, it's real. And then they do a series of these sorts of things, and what it shows you is the Bohmian trajectories of the electrons going through the slits. They're doing statistical. They have to repeat the thing over and over. You get a lot of measurements, and that's what this shows. It actually shows the Bohm particle paths, which Bohr said you couldn't do, and it's experimental. And they've done it with photons too. It's beautiful, but I don't want to waste time. We only have an hour. You look at Ephraim Steinberg. I'll send the references, and you could see the details. There's a lot of stuff. They're actually doing very precision optical measurements with this technique that you couldn't do before. Even higher resolution, beating the uncertainty principle kind of stuff. And this is a practical thing. This is of practical importance for technology. It's not just theory. Okay. All right. Now let me get to. I want to go more about the post-quantum theory. This is new physics. This is beyond anything you're used to. Okay. Sutherland had it right. No need for configuration space to handle entanglement. Okay. That's a big mathematical convenience. Bohm pilot wave theory is made relativistic using a variation on Aharonov's retrocausal weak measurements in the Lagrangian-based action principle of Einstein's block universe, of Minkowski block universe. Okay. Now this is the new stuff that you guys don't know really anything about, because this is a new thing, you haven't been taught it. The problem is that nobody in the textbooks, everything all of you have learned, you've never had a course in Bohm pilot wave theory, and you've only had the Copenhagen interpretation, which are only quantum waves, there are no hidden variables, okay? And even if you've had a course in Bohm pilot wave theory, you still won't know this because they don't know. It's a result that's been kind of glossed over. It's in Bohm and Hiley in their undivided universe. But what happens is that even in the Bohm pilot wave theory, the quantum potential, or the quantum information field, the wave modifies the motion of the particle, but it violates the action-reaction principle, the philosophical. There is no feedback of the particle's motion back on the guiding wave that's guiding it. So let's think of a philosophical generalized action-reaction, so that the Bohm theory, and this is true of ordinary quantum mechanics, the wave acts on the particles, but there's no feedback control loop, okay?
So what Jack's saying, because he explained this to me last night, is that Bohm's theory is deterministic, but this, when you incorporate feedback loops in both directions, it cannot be deterministic.
No, that's an important point. Keep this in. I'm going to keep coming back to that point. All right. So now, but let's think back to relativity theory. Special relativity does not have gravity. What special relativity does, the space-time geometry influences the motion of a particle that doesn't feel. If you have a neutral test particle, a neutral, no charge test particle, it follows a geodesic in the flat space-time geometry. So that's geometry there is like a pilot wave, is analogous to a pilot wave. And of course the geodesic is trivial because it's a straight, what you learn in elementary physics, straight line, constant speed, no acceleration, okay? So there, but if you have large concentrations of mass, energy, it doesn't modify, the space-time is rigid. The space-time is rigid in special relativity. Gravity is the effect of action-reactions, the effect of the reaction of mass energy back on the geometry. And it took, and that plus the equivalence principle, Einstein needed the equivalence principle, he needed action-reaction, and he also needed the formalism, the tensor calculus, which he got from Marcel Grossman. Rod Sutherland is my Marcel Grossman, giving me the math that because I had the idea, but for 20 years, but it took 20 years before Sutherland did this. All right, so Einstein's action-reaction organizing principle formulated as part of the non-statistical post-quantum weak Lagrangian connecting the pilot wave to its beables or hidden variables. Now let me say one other thing. This is very important for quantum computing theory because you all know about the no cloning theorem and the no signaling theorem. That entanglement cannot be used as a direct command control communication channel. You always need, or say in terms of coding theory, you need some kind of classical key to unlock. You can put complicated information non-locally or globally in the entangled network of particles. You have information there, messages, meaning, all your code words and your symbols, your language. Yeah. But locally, if I say, make it real simple, if I just have two correlated particles, no matter what I do over here, I won't be able to see that wiggle over there. All I see here locally is randomness. It looks uncontrollable local randomness, so that by wiggling here, I cannot send a message to the guy. Alice, by wiggling here, cannot send a message to Bob until she also sends something else. This is quantum teleportation, quantum cryptography. Until she sends, a classical key to unlock, to decode. It looks random, but if you have the key, you can get the message. And that's the whole quantum cryptography. The Chinese, by the way, the Chinese are building this big thing. They don't realize I'm going to be able to hack. See, there's the possibility we can actually hack into supposedly quantum cryptographic networks. They are the Maginot Line of quantum. That's why the CIA, of course, and the NSA are really interested in what I'm doing. And so are the Russians. By the way, I've been interviewed by Putin's people too. That's a whole other story. This is hot stuff. Okay? Now, so the point is that in the quantum limit, this is not all there is to go from post-quantum theory back to ordinary quantum theory. There's one other assumption, which is not obvious here, but there's more. You have to take the action-reaction part of the new Lagrangian that Sutherland wrote down. That action-reaction part has to go to 0. And when that goes to 0, you get back to no signaling. You get back to all the ordinary quantum teleportation, quantum dense coding, all that stuff. The reason you cannot the reason you cannot know the future, the reason that you can integrate here, this sort of gets back to this question. The reason you're justified in doing the integral over f is because you're in the limit of 0 action-reaction. And in that case, you cannot decode messages from the future, backward in time messages. So that would mean that all the people who have precognitive dreams and precognitive remote viewing, that wouldn't work. Unless, the only reason it does work is because of action-reaction. When you have action-reaction, then you can do it, and you no longer do the integrals. Because there is a particular f you can actually perceive, you see. You have knowledge of f, and that's from action-reaction. All right, so that's very important. So in post-quantum theory, you can use entanglement as a communication system, and we know from the communication can be anything. It can be from the past to the present, from the future to the present, or between what looks like fast and light. They could be separated, fast and light, whatever you want, because of the zigzag. It doesn't matter. So this is big. This is extremely important. All right. Yeah.
I'm sorry. Are you familiar with the Wheeler-DeWitt equation?
Yes, of course. Yeah.
How does that relate to what you're talking about?
The wheel. Okay, a good question actually. And there's a whole bunch of papers. There's a guy named Sheldon Goldstein at Rutgers University, and he's talked about the Wheeler-DeWitt equation. It gives a illusionary. It gives the so-called problem of time. What happened to time? And that's because they've neglected the hidden variable. They've neglected the Bohm. In the Bohm picture, there's no problem. In the Bohm picture, the quantum information fields are time independent, but the hidden variable, which is the three-dimensional classical space geometry evolves through time. It's like the particle moves through time, and that problem. The reason for all these guys doing quantum gravity, Wheeler-DeWitt equation, and all the standard stuff, they just don't know. They just have the wrong physical picture, so they have these problems which are pseudo problems. Okay, so it's all bullshit basically. All right, let me get. I mean, because if you assume there are no particles or no classical geometrodynamic fields, and then you're going to get in trouble. And in fact, they do. So but the problem is trivially solved. No longer, it's a non-problem. Okay, let's get on. Oh no, I want to go the other way. Okay, I just want to show you a few more. All right, now, this is important. This is all in Sutherland's papers. You read his papers, and I'm just like extracting a few key ideas. So when you read Sutherland's papers, you really have to study this stuff because it's an unfamiliar way of thinking. This is for particle quantum mechanics, or particle post-quantum mechanics. This is for a particle, like a point particle, this is its four velocity. Everything special is relativistic. This is the actual classical velocity of let's say a point particle. If it's an extended particle, we're talking about the center of mass, the point like center of mass motion, neglecting the internal degrees of freedom, okay? So this is that. This, and you have to read, I'm not going to go into details, this is what looks like the wave in ordinary quantum mechanics, except it's with this new, it's this kind of object, it's a weak value. This is the pilot wave current density, okay? But it's non-statistical, it's at this level now, we're working at this level. We haven't done any more, we haven't integrated out the future. This is all now post-quantum theory. So this is the post-quantum value of the electron current. It's a 4-vector, and this is its the fourth. This is its invariant magnitude. This is if you take J alpha. If you rho 0. Okay, rho 0. Rho 0 is the square root of J alpha, okay? So this is the standard thing. This is what you normally think of as velocity. Now, it turns out this factor, and this is beautiful. I see this, this is Sutherland's now genius, so he doesn't quite realize the physical significance, I think, what he's done. I think he was contacted by, he's a sleepwalker too, He doesn't, good. This quantity, this factor, is a factor in the action-reaction Lagrangian, okay? And when it is 0, you have to take this, you have to assume this is 0 in order to get back to quantum mechanics, okay? But when it's 0, what is it? When it's 0, it's the de Broglie guidance equation. And physically what it means is that the particles are constrained, and the gradients of think of the wave, the quantum waves, think of them as like quantum hydrodynamics, as a fluid. Okay, think of it as a fluid. So these are the gradient flows of the fluid, and the particle is trapped in the grooves, in the gradient grooves, okay? That the particle velocity is how many of you have seen superfluid theory where like the superfluid velocity is the gradient of the phase over m, h bar. You've seen, it's like, this is like in a particular case, is a special case of this equal to to zero. And that corresponds to zero back action. Now this is very important conceptually, because that means it's only under those conditions when there's no action-reaction between waves and particles that the particles are truly hidden. That's why, that's why you get away in doing correct calculations and getting the right energy eigenvalues of atoms and doing the transition probabilities, the S matrix, the cross sections. All that stuff works only using waves, because in that limit, the extra degrees, dynamical degrees of freedom, so-called beables by John Bell, or hidden, except they're not really hidden variables by Bohm, that they really are hidden. They're under they're so to speak under the skirt of the waves. They're trapped in there. But in the new thing, they're no longer. They break out and they become directly observable. You see, this is very, very important. And by the way, why plus and minus? Guess what? This is also very important, because it turns out that, and this was kind of well known even in Bohm before all this stuff. Like if you try to do the Klein-Gordon equation in the Bohm theory, in this quantum, without the action-reaction even, what happens is that these streamline flows break outside the light cone. They become fast and light, tachyonic, and also, but not like Feynman, not where it's a point thing. It's more like string theory, where it curves gently, and it even goes backward in time. Okay, and then the plus and the minus take into account in the weak. Now you can actually see this in principle. If you do weak measurements, you can see the particles going fast and light, or backwards in time even. It's not the same. It's not the same as Feynman, where the antiparticle propagating forward in time is a particle going backward in time with negative energy. It's different from that. Okay, it's different from that. But what happens? But this has been, and Sutherland explains this beautifully. By the way, you have to study. You have to do some work here, homework to really get it. He shows that when you do, if you only look at the strong measurement result, this anomalous effect cancels out in the statistics. But if you do the weak measurements, you can actually see it. So it's actually observable in principle. I mean, experimentally, it's not okay. So that's a nice thing. All right. So what did I just do with the control? Oh, all right. So now, almost there. Okay. So for example, look. Here's an example. Here's an Euler-Lagrange equation. This is the Dirac equation for a neutral particle. This is spin 1/2 Dirac equation. The left-hand side is your normal single particle Dirac equation, only for the history states. This is propagating forward in time. There'll be a corresponding equation for the final state. There are two equations. I only wrote down. You can imagine the other one. Okay. Here's the new effect. Here's the new effect. This is all defined. Just read this paper. I'm not going to define all this. Here's the new effect. This is the source term. This is the feedback control term. There you go. This is it. This is it. So, and this is called the source term. If you look in ordinary books, they say, well, quantum mechanics doesn't have any. The wave function doesn't have sources. Here it has. This is what Clea likes to call your feedback and control term. There it is. That's it mathematically for the Dirac equation. No bullshit. Very precise. Okay. And when you take this is we haven't put charges and vector potentials, but you set this thing equal to 0, you get back to ordinary Dirac theory. Okay? So now, we could start doing quantum field theory this way. By the way, what's going to happen? Feynman diagrams. Right? Feynman diagrams are only for waves and no particles. These are extra degrees of freedom. And this is a problem. This could be a research problem for some of you guys in graduate students. This is, how does the Feynman diagrammatic technique get modified by these new degrees of freedom? Okay? This is going to change. There's new stuff going. There's going to be new kinds of, there's going to be a generalized Feynman diagrams that will reduce the ordinary Feynman diagrams when this back action, this is the back activity term. When that's 0, you get back to the old theory. So in order to get ordinary quantum theory and quantum field theory, you have to both assume this is 0 and also, but you see, it's consistent. When this is 0, you don't know the future. If this is not 0, this thing breaks down. You can't do the integral. You have to use this directly. This is directly observable. Of course, now the good question is, when does it not become 0? When does it not become 0? Okay, now this is a Dirac equation for the pilot wave with the source term from the actual particles. This is a feedback control loop between the waves and the particles. They're self-organizing. They're self-organizing. This is just what you want. This is what we all want. Okay, now, and here it is for the Dirac theory. He has Klein-Gordon. You can do spin. You can do spin 2. You can do gravity. Whatever you want to do. Okay. This is the action principle, Feynman-Schwinger, and with with a few extra dynamical degrees of freedom. This is all very standard mainstream stuff. Lagrangians, actions. Okay, so let's go down. Okay, well here just this defines this. I'm just defining that. You could see this on your own on your computer. It's all in the references. Let's go down again. Now look, there's something else. The Dirac equation tells how the particle changes the motion of the waves of the Dirac spinners. But there's also how the waves move the particles. This is dynamical equation for the particles. And look, it looks kind of like the Lorentz force. A little bit like the Lorentz force. Right? Look at this. See, here's your velocity. This looks very much like classical electrodynamics, but it's not. It's post-quantum theory, right? I mean, it's beautiful. We could do computer simulations and you can solve problems. And this is the acceleration, the proper acceleration of the particle. But it's mixed with the wave. And this is like a gradient flow. Yeah, gradient flow. And this is like a torsion, a curl. This is like the curl.
What's interesting is the hydrodynamic aspect, because a lot of people think that a proper quantum gravity theory will behave as a space-time quantum superfluid.
Yeah, well, yes. I actually had that idea many years ago. But yeah, of course, yeah. The answer is yes. I agree with that. But this is another. So that you have the two. So in the Dirac case, you have now a complete set of dynamics. You have how you need this to get your feed. Now you have the feedback loop that can be calculated. You can have people who know how to do Mathematica they can sit down and start doing problems. I can't. I don't.
Can we extrapolate you or me on why a feedback loop would necessarily be non-deterministic?
Yes, that's clear because. Whoops! What happened? I stepped on something. That's because. Okay, let me. Okay, I will. Let me get back to that. Let me finish this. And let me get back. That's an important issue. This is an important issue. This goes to Penrose's stuff on strong AI. This has to do with artificial intelligence. That's a key question. I will come back to that. Let me just see if there's anything else I want to talk about here. So now you have two sets of equations here. This is the two equations together are a feedback control, self-organizing loop of post-quantum mechanics. Okay. Okay, so the pilot continuity equation now has a new source term. Therefore, the Born. This is another thing. Okay, you can get the. Okay, if we go back to the Dirac equation, if we separate the Dirac equation into real and imaginary parts, okay, then I forget what it's really one of those is like a Hamilton-Jacobi looking equation for the phase. Okay, this is an ordinary quantum, it gets more complicated in post-quantum mechanics, but similar. And then the other equation is your continuity of flow equation. So it looked like that. It's not quite that, because that equation I wrote for the particle with the curl and all that, that's a separate equation from the continuity equation. This is, okay. But the pilot wave now this is very important. This is non-unitary time evolution. Has to like dissipative structures, okay? But that's biology. We're beginning to get into biology now. The pilot wave continuity equation now has a new source term. Therefore, the Born probability current density flow, which is waves only, is no longer conserved because there's these new degrees of freedom. It's a reservoir. It's a reservoir for wave flow. From these hidden variables, it's like a pump. It's like a reservoir. Okay. The time evolution is non-unitary, as in pumped open dissipative structures. See. This is actually pretty cool. The theory is the theory is highly nonlinear. It's highly nonlinear because of the adaptive self-organizing two-way relation between pilot wave and its variables. Okay, and then you can actually see this. It's like general relativity is nonlinear. This is a nonlinear post-quantum theory. And by the way, the general theorem, Steven Weinberg and other people have shown, as soon as you have nonlinearity in this sense in quantum theory, signaling becomes possible. Entanglement now becomes, okay, they're saying entanglement is an important quantum computing resource and quantum information resource. It's even now more important because now it's directly, locally decodable, keyless, locally decodable entanglement signaling. It's happening in the brain. It's happening between the neurons and in the brain. See, there's exchanging information. Obviously, if you could do that, it'd be better than not being able to do it, right? Okay, all right. So, okay, this. Okay, no violation of Einstein's special relativity. This is him. Okay, and again, the action-reaction unhides the BBOs. The paths are no longer coincide with the pilot wave streamlines. All right, so, and by the way, this is all, you read this on your own computer. It's all in the references, okay? It's all up there on the web. So let's go to the final, no, I'm going the other way. And there, okay, so I think okay, post-quantum theory is the quantum theory as general relativity is special relativity. So what happens in general relativity, you let the fourth rank Riemann-Christoffel curvature tensor vanish everywhere, and it's basically special relativity. Okay? Here, you let you somehow or other suppress the action-reaction self-organizing loops between waves and particles, and that's what everybody has been stuck in. That's their little box that the conventional quantum community are in that box, especially people from Copenhagen. Okay? And they're in that box. I've just opened Pandora's box.
I will even probably say beyond the vast majority, 100% of the experts working in quantum computing,
they don't know this at all.
Are not considering this. And
they have no idea.
If this back reaction is real, then I don't see how you can successfully approach the limit of really exploiting quantum mechanics for the purpose of quantum computing without considering this if it's real.
It's definitely real. It'll be real. And what we have to do, though we have a big opportunity here, as you know. I mean, we have, without getting into the woo-woo Twilight Zone stuff, because Google, all of them, or whatever, who's working on all this?
Microsoft, IBM, and Google.
Microsoft, IBM, Google, Apple,
and
China. They are totally clueless. And they're going to go around, they'll do some interesting things, but they don't have it. We have it. And the thing is this, all these systems they're making, they're in thermodynamics, well, we have to think of a laser. This is my version of a laser. We have to make open dissipative structures. You know what happens in a laser? You need a population inversion to get the coherence, okay? And so you have to keep pumping until you pass a certain threshold, and then you get this coherent lasing effect. In a similar way here, in the living system, there are open dissipative structures, and the metabolism, all the chemical, whatever, I don't even know. I mean, you guys probably know it even better than I, but some of these biological details. But that German guy, he knows all this stuff. We have to get him. And this is Fröhlich, Herbert Fröhlich, who I knew. I actually worked with him at UCSD. He has a model of a biological membrane, okay? And they're just what they are is just a bunch of electric dipoles wrapped in a cylinder. This is getting into all Remy stuff, okay? Wrapped in a cylinder, but it's being pumped with energy, external pump energy, and he shows it reaches a certain critical threshold.
Pulse is like a laser.
It coherent, the phonons, the vibration. Oh, the dipole become a coherent, like a coherent excitation wave, long range wave, coherent signal. There are like elementary collective modes of all these little dipoles. They're like phonons are to crystal vibrations. These are to the, and he shows that, and that's very important. So the point is, we can start building stuff. We can start making nanotechnological models of these Fröhlich membranes, pump them with energy, and even take your quasi-crystals too, pump it with energy. You got to make it into you have to take it far away from thermodynamic equilibrium. And these effects are going to come into effect, you see.
Would you mind if I just insert a 2-minute comment? It's very supportive of what you're saying, but So we have an object to explore, which is an Empire wave. So most of you know this, but I'll say it briefly. So we take E8 because we want to recover those gauge symmetry physics. We project it to the Elser-Sloan quasicrystal in 4 dimensions. Now there is an object. It's not exactly like Einstein's block universe space-time. Any one of the Fibonacci chains that composes that 4-dimensional quasicrystal, when you do what we do, which is we take a 3-dimensional slice of it, which means that you have different 1-dimensional quasicrystals that have cut through the 4-dimensional object. So then we take that object, that 3-dimensional slice or subspace of the 4-dimensional quasicrystal, and you have to understand that even though it's a 3-dimensional slice, its Fibonacci chains were participating in running through multiple time slices, if you will, in the 8-dimensional space. Now, that 3-dimensional thing, which crosses different times, is compounded with our 4-dimensional related rotation in 3 space. So in other words, in the QSN, you have these 1-dimensional lines that are natively part of a 1-dimensional quasicrystal that ran through multiple time slices, right? And so anyway, so then, because it's a quasicrystal, and a fundamental thing about quasicrystals is the empire and the special density of beams of the tiles in the quasicrystal drop in density with distance. So as you animate out these quasi-particle patterns in the QSN by phazon codes, which is essentially your language legal inflations on the space, on the denser possibility space, and once you make patterns, quasi-particle patterns like that in the computer, and then understand those patterns algebraically, what you have is an object called an empire wave, and it's complex, not necessarily as in complex numbers. It's complex, and whatever it is, let's see. This is a fact that there's an empire wave. We have to figure out how to use empire waves interacting with one another quantum mechanically, or it will not behave deterministically. It will have the empire wave of 2 particles is going to influence one another. Furthermore, the empire wave of a single electron is going to self-interact with the electron itself.
Let me get back to your original question.
So the empire wave is very, very analogous to Bohm's pilot wave, where it is a system of a wave. In Bohm's idea, it's a system of a wave and a particle interacting, where the wave guides the particle, and the particle can even influence the wave. But we've always had one big problem with Bohm's idea, which is that it's deterministic.
Yeah, okay.
And in ours, it can't be deterministic.
Yeah, okay, now let me explain all that, because that's... Okay, what determinism means, this gets back to Roger Penrose. If you read The Emperor's New Mind and all his popular books, he talks about this. The question is now, even in biology, is consciousness deterministic, or is it computational? All the AI programs right now, they are computational, obviously, and they're using classical computers. Even if they use quantum computers, I think they still, well, there's not...
There's no artificial consciousness.
Yeah, but okay, right.
Yeah.
But let me tell you what does determinism basically means the same thing to me as an algorithm, okay, or as computable
Deterministic algorithm.
Deterministic algorithm. Even if it's stochastic, it doesn't make the hell of a difference. The point, the essential difference, is that think of a Turing machine. Okay, Turing machine, right? Classical Turing machine, it's step by step by step, one direction time. It's even quantum statistics, even quantum Turing machines will have the same limits. And it's still okay. What's happening here in the post-quantum with the back reaction is that both the future and the past are influencing what's happening there and what's happening in the present is self-organizing because it's getting, both things. I mean, his equations show exactly in detail how it happens. And that transcends determinism. It's no longer, but what it is, it's like you had this in your video. It's a self-consistent loop in time.
Right.
It's a it's a loop. And remember, she said that part was I want to use those.
Maybe I could suggest a clean definition of determinism via Conway, which is determinism is defined as an event which is strictly determined by the past events.
Right.
Really
Right. And that's no longer true here. But let me tell you something even more exciting. Something even more exciting than that. How many of you have heard of the world hologram theory? How many of you have heard of Susskind and ER equals EPR? Oh, all right. You're familiar with that, right? Well, if you look at my book, this crazy cartoon book that sold hundreds of thousands of copies and influenced Hollywood movies like Back to the Future. I'm the guy from Back to the Future. I'm the crazy time travel scientist. I was working. I knew Coppola and all his Lucas and Spielberg in the 70s, and that's it. Yeah, I'm not. Yeah, no. Hey,
grow your hair.
Yeah, no, because okay. Do you remember how that movie opens? The first one. Remember with Michael, whatever his name is, on the surfboard. Yeah, Michael Fox with the big loudspeakers. You'll meet this guy. Kim Burafato was my sidekick at the time, and we were living in North Beach, and he was living in this hotel. He had these huge speakers. And he used to play rock music, and the entire North Beach, Grant Avenue would hear for about 2 or 3 blocks around. And Lucas and Spielberg and Coppola would all sing at the Savoy Tivoli, and they would hear this stuff. And they were laughing there. And then Kim, he was a really good-looking guy. He was a Navy veteran, but he looked like Don Johnson. Movie star looks. And he was he had Navy SEAL training. He would come up on his short pants, the little bicycle. But they took Kim. Everybody knew about Kim. He's a character. They took him riding the bicycle. That became Michael Fox riding the surfboard, and with blasting. You see, that's where that all came from. That's the hippies say. That's all in hippie say physics. So there was, all right, so what was I talking about? Oh yes, ER equals EPR. Okay, in my crazy book, Space, Time, and Beyond, I have the beginnings of ER equals EPR. I say, hey look, on one hand we have quantum entanglement, EPR, and the other we have Wheeler quantum gravity, these wormholes, okay? And somehow they must be dual aspects. I mean, it's in the book. They must somehow be connected in some deep way. Now, I didn't, that was a primitive thing. Now, only recently, okay, now here's the thing. Oh, okay, now I need that picture. I need the references. I'm going to show you something about E equals EPR, because what happened, this is beautiful. When you have back reaction, when you have entanglement messaging, that is the EPR, right? But it's signaling EPR. What does that mean in terms of the wormholes? They're traversable wormholes. Particles can get through. So it turns out, okay, now listen, there's the direct connection. If you, in post-quantum theory, it corresponds to particles moving back through traversable wormholes, the little time machines. That corresponds to what Seth Lloyd at MIT and even David Deutsch said, all this stuff about if you have closed time-like curve computing. It's definitely non-deterministic, but it's super powerful. Okay, and right away, so we have 3 of them.
Reminds me of the time crystals of Frank Wilkes said.
Yes, so we could do all that. We could do time quasi-crystals. We're going to pump them with energy, and you're going to get everything you want. So the point is that, to recoup, the computers here, they're all classical computers. They operate 1 billion time. And as Penrose points out, in terms of the mathematics, they occupy a very small degree of solvable problems. Penrose is really, I agree, everything Penrose says about this is right. Okay. Then you have quantum computers. Quantum computers are supposed to be more powerful than classical computers, right? That's the whole deal.
They do things that classic cannot do, but they haven't done that yet.
They haven't done, right. But I'm talking about the third, this is why I call it the third revolution. It's the post-quantum computer can do things that a quantum computer cannot do. And it solves NP equals P. I mean, it's computing back from the future. And there are all kinds of papers, by the way. There's a whole bunch of literature about CTC computing and how they're more powerful than quantum computing forward in time, okay? So that's what we have here, because E equals EPR. Okay, where's this? Let me just show you something. I want to now get back to,
Horizon picture?
Yeah, the horizon picture, yeah. Okay. Now I'm going to give you a picture of the conscious universe. Okay, right, okay, okay. All right, now look, this diagram comes from the PhD thesis of an Australian woman, Tamara Davis. She worked with Davies, PW, Paul Davies. Yeah, Paul Davies. And this is a 2004. This is from a PhD. I modified it a little bit. It's okay. What she did at the time, she took all the best information from the standard cosmological model. They knew about dark energy then, about the Sitter space and all that. And she did a computer simulation of the universe. But this is like a Penrose conformal diagram. It's not quite it's Penrose like. It's a conformal. This is conformal time, right? Conformal time. And from the dark energy density, you can compute that in our actual observable universe, okay, even though it's infinite proper time, corresponds to a finite conformal time given given the observable data, the energy density of the dark energy. You've got to read her thesis, beautiful thesis. She won an award for it, by the way. Okay, so that corresponds to about 64 billion years of conformal time from the beginning of the universe to the end of the universe, in a certain sense. Now, let me give you a physical picture. Proper time. What is proper time? Proper time is what you measure with a spring, right? That's proper time. So what about Penrose's conformal time? It's a mathematical, just stereograph, whatever he does, beautiful math. But physically it has a simple explanation. Physically all it is you have two mirrors, and they're in the Hubble flow. They're at rest, they're what's called co-moving. This is the co-moving, this is the Hubble flow. The universe is the space is expanding, but it's also accelerating in this picture. It's accelerating. You have dark energy, anti-gravity, it's accelerating. And so you have the two mirrors. They are locally at rest in the Hubble flow, and you're exchanging light signals between them. So you can see they're further apart, so it takes longer. So you can see, and the way it happens, you get even infinite spring time is a finite mirror time, conformal mirror time. Okay, one of the important thing. Now you learn in special relativity there's no absolute simultaneity, and you also learn there's no absolute rest frame. Right? That's special locally. Remember, in special relativity is a local tangent space limit of the global general relativity. Okay, but you also learn about spontaneous broken symmetry, right? You know that in ferromagnets, in crystals, in quasi-crystals, both space and time, what you're doing, you're spontaneously breaking down a dynamical symmetry in the ground state, in this complex ground state. The ground state no longer obeys the symmetry. You haven't violated the theory because the action is still invariant into all your symmetries, but the particular solution, the ground state, is not. Okay, and that's what ferromagnets are, that's what crystals are, including both crystals and quasi-crystals. They're all examples of spontaneous broken symmetry. And by the way, even the superfluid spontaneous broken symmetry, we talk about the superfluid vacuum, that's what we're talking about. It's spontaneous broken symmetry. The Lagrangian, the theory itself, dynamics is still invariant, but this particular solution. So now, in our standard model of cosmology, we have absolute rest frame. I mean, we do have a preferred global frame. Global. It is the frame at which the Doppler shift, if the Doppler, it's maximum that the black body radiation, the cosmic radiation, is maximally isotropic in all directions in the sky of the entire 4 pi thing in the sky. If you see that there's a asymmetry, you see there's a blue shift here, a little red shift there. If you see an asymmetry, you are moving at a velocity relative to the Hubble flow, which is spontaneous broken symmetry of general relativity. Okay, so you actually have an empirical, measurable definition of absolute rest at that level. Also, you also have absolute time. You have the time from the Big Bang. And how do you measure that? It's the temperature of the black body radiation, right? So that's so. For example, we could have a starship. We could have a Stargate, a big traversable wormhole, and Klee goes out to one of the habitable exoplanets with Elon Musk, who wants to go with you, right? You go through the rain. They go through the Stargate, and it takes you maybe it takes you 5 minutes, through the wormhole to get there, and you're there. But we could still compare. We know we have an absolute global simultaneity because all you have to do is measure your local black body temperature, and I measure my black body, and if they agree, we know we're kind of simultaneous. Right. But we'll also know if yours is cooler than mine, you're in my future. Suppose you're an immortal God and you live forever, okay? And this is the moment of inflation, the Big Bang, and this is your world line throughout time, infinite world line. This is your immortal God, okay? And then this thing here, this is the omega point. That's the alpha point. It's all observer dependent. See, if you move, different observers will have it somewhat different. This is called, this thing here, the orange, that's called our future de Sitter dark energy horizon. Okay? Because the universe, because space is accelerating in its expansion rather than slowing down, eventually it outpaces light signals, so that this is a boundary we cannot ever, no matter where we are, we can never see beyond this horizon, the future horizon.
Isn't it currently outpacing light?
Well, no, wait, no, we're right here. We're right here.
Right there.
That's us. That's us. Yeah.
I'm asking. Right now, isn't it?
Well, okay,
isn't the
wait.
expansion faster than light now?
No.
Or no?
Okay, wait a minute. Space, there's no limitation on the speed of the expansion of space. It's only particles moving within space. Yeah, of course. Everything is, well, I don't know.
Faster than light, I was just wondering.
Well, I'm not sure how you measure that, but the point, light, the speed, there are little light cones in here, and no particles go faster than light, except they're quantum, let's not get into that because it's a side issue. It's important, but it's a side issue. I'm taking away from the key point. Okay, so this is what's called our future horizon. Similarly, there's also a past particle. That's the green dot, past particle horizon. Okay, and now in the past particle, see here we can't. If we have something here, we can't see anything. But when it goes, well, actually, no, we can't see here. But let's look at this one. Oh, well, I'd have to imagine one like here, one here. Sort of go like that. In any case, this is our past part. So this is a sandwich. It's called the boundary between our future event horizon and our past particle horizon. That's our observable universe with light signals. Okay? You can never see outside. Nobody can ever see these regions here with light signals, limited speed of light. Now, if you have wormholes that can punch, that's different. Just talking about conventional astronomy. Okay? All right. Now, however, look here. See, here's our future light. Here's our future light cone. The light travels at 45-degree angles in this conformal diagram. Okay. So we could be getting information from this point back to us, and here we could be getting information from here, from us. Okay. But now, here's the point. In actual physical space, this point is really a two-dimensional closed surface. We're inside it. We're at the center of this surface, so to speak. Okay.
Right, so it's a two-sphere surface.
It's a two-sphere surface. But according to Seth Lloyd at MIT, the black hole computer guy, all this stuff, and because of the Hawking entropy area horizon, all that, black hole thermodynamics, and this involves also the EPR hologram universe idea. Here's the idea. The idea is that this here, that sphere, it's a huge, that we're in the center of, is a quantum computer.
It has a thickness.
Oh, well, okay, but wait, there are two. These guys are only thinking surface. They don't even take it. They didn't even thought about thickness. That's what Cynthia and I have done. Okay, thickness. But even let's forget about the thickness here. Just let's talk about the surface.
For us, the sphere is a quasi-crystal, and it is.
Okay, but wait. It may be. Now wait. Just wait.
I'll talk a little bit about.
Okay. Yeah. But wait. Let's. This is. I want to stay focused like a laser here. You're going off topic. It's interesting. I agree. But let's just stay on this track. Okay. I'm trying to make a point that none of you realize. Okay. That is that. So this thing is a computer. Now, according to the hologram, the Susskind, by the way, Lenny Susskind and I worked together at Cornell back in the 60s. According to these guys, it's a conformal field theory on the horizon. It's a conformal field theory, EPR correlation in a conformal field theory, and I think isn't there a connection to quasi-crystals, conformal, and whatever. But yeah, it could maybe a quasi-crystalline lattice on the horizon, sure. At the Planck scale, absolutely, I agree with that. That's quantum, that's happening there, I agree with that. And also, it's very high energy radiation, but it gets redshifted by the time it reaches us. So it goes down. So this is how you get down from your high energy Planck to out to our biology. See, this is very, very important. And so it's a computer. But if it's a if the action reaction, if it's a post-quantum computer, I'm saying it's a conscious. I haven't had enough time to get into this. It's a conscious computer. The reason being that assuming that quantum pilot wave, quantum information is thought fields, not necessarily conscious. In other words, if you ask Sir James Jeans, looks more and more like the universe, great thought rather than a great machine. Well, he was using Copenhagen. It's both. The universe is both a great thought and a machine and a Newtonian machine. It's both.
Thinking machine.
Yeah. Well, it's both because that's the Bohm picture. But the point is that here's the theory. If you ask, what is there in physical reality that corresponds to thinking, the thought, the mentality? It's the quantum waves. That's it. You assume that. That's just the way Clee says, code theoretic axiom. Let's assume to see where it takes us. An ansatz. Educated guess. My educated guess. And it's the same that Bohm and Bohr, and they all had it in a way. They just didn't clearly say it the way I'm saying it. Okay? If we make that assumption, what is consciousness? Consciousness is the back reaction, the signals, the environmental signals, the back reaction, the source term in those equations. It's just like
and the forward, meaning it's the field.
Yeah, but it's going both ways. Yeah, and it's all self-oriented. Yeah, all that is there already. And it's like, with a battery, voltage differences are important, right? Not the absolute voltage. Same way, what we are experiencing in our inner thought is how the material world is changing the patterns in our thought wave. Now, what our minds are, what this mind is, it's a coherent, and actually it's going to be an advanced one, and it's going both ways now. It's an advanced destiny coherent field. It's a Higgs field. It's like it's a spontaneous broken-symmetry. It's coherent, long-range coherent. That's the binding problem. And so we have two of them. The history one is our memories. That's where our memories are. Okay, so I'm going down. And the advanced one, that's our creativity. That's our vision. Literally, it's all precognition, right? So, and that's Mozart says, how do I write? I don't know. I just hear it.
Remembering forward.
Remembering back from the future. That's how all creative people do it. I mean, I never know what I'm going to write. It just happens, right? That's anybody. Artists. I mean, when Michelangelo was doing the stone, it was just the stone was telling him what to do. Mm-hmm. So this is it. I've just given you the mystery. This is the final secret of the Illuminati.
That was very good.
Okay.
Very exciting.
Okay.
I'm gonna meet